Okay, this is Math 1090, section 1.4 on linear functions. Let's get started. First, the definitions. A linear function is a function whose graph produces a line. Linear functions have a constant rate of change and can be written in the form f of x equals mx plus b, or f of x equals b plus mx. So typically, most textbooks probably use the first form, which is often called slope-intercept form, because the m is the slope and b is the y-intercept of the line. Your author for our textbook prefers the second form, the f of x equals b plus mx. I think he prefers it just simply because it's kind of more like how you would read it if you were to read the function from left to right. It kind of makes more sense to him. But anyway, what about that slope though, that m? Well, that m is called the slope, or a constant rate of change. Okay? And so the second definition here is the constant rate of change between 2 points, x1, y1 and x2, y2, can be calculated as the ratio between the change in output to the change in input, or we often use the Greek letter delta to represent the change. So delta y over delta x, where change is measured by computing a difference, by taking how different two values are by subtraction. And notice the formula here has y2 minus y1 over x2 minus x1. But does the formula know which point you're going to label as point 1 and point 2? Or does it matter? An important thing in math is that whenever you give a name to something, that name should be irrelevant. So which point you call point 1 and which point you call point 2 is completely arbitrary, right? So it shouldn't matter, and it doesn't. You can check that out if you want, but this formula, it never matters which point you call point 2 and which point you call point 1. As long as you're consistent and always put the y value of the point you're calling point 2 first over the x value of the point that you're calling point 2 first. And then you use the point 1 values, you subtract those off. As long as you're consistent, you'll get the correct slope. Okay? Of course, you should do a little sanity check though, and your slope, the value you get should be greater than 0 if there's an increase between the 2 points. In other words, if the line that you draw between the 2 points trends upwards as x increases. And then if m is less than 0, the linear function will have a negative rate of change. This means that the y values will decrease as x increases. So you should make sure that you always do that little check. Do I have the correct sign to my rate of change or to my slope? Okay, let's do an exercise. The pair phone company knows that to produce x equals 580 pair phones, it will cost y equals $41,720. To produce 960 pair phones, it will cost $64,140. Compute the slope, the rate of change, of the costs and include units. Okay, so what we're doing is we're relating x to y, or quantity to cost. So we're creating a cost, we're finding the slope of a linear cost function. So we're given 2 data points that lie on the line, on the graph of the cost function. So what are those 2 points? Well, the first point is when we produce 580 phones, it costs $41,720. And we also know that when we produce 960 phones, it will cost us $64,140. Now, which one of these points I call point 1 and which I call point 2 is irrelevant, but I'll just call this point point 1. So I'll label this as x1, and this will be y1. And this I'll denote as x2, and this will be y2. Okay, now to get the slope of the linear function, remember that the definition is that the slope is the change in y divided by the change in x, or delta y by delta x. And what does delta always signify? A difference. So we want to compute y2 minus y1 over x2 minus x1, which is 64,140 minus 41,720 divided by 960 minus 580. Okay, what is that? I'm going to pull up my calculator to help me with that. Actually, let's do this. So I want to do 64,140 minus 41,720. That's a difference of 22,420. And let's see, 960 minus 580. I could probably do that in my head, but I have the calculator handy. It's 380. And let's compute that quotient. So 22,420 divided by 380 is 59. Okay. Now we want to attach units to this value. What are the units of this rate of change or slope that we just computed? Well, the rate of change will always have the units of the output over units of the input. Our output is in dollars and our input is in number of phones. So what this gives us is the cost dollars per phone. So the answer is the slope is $59 per phone. Okay, moving on. The following graph gives the total cost C in dollars for producing ski goggles as a function of the quantity of goggles produced, X. So we have a function C, cost, is a function of X, quantity produced. Okay, and we have a graph, and we're asked to determine the slope of the line. Well, we have 3 points on the line, but it doesn't matter which 2 points we pick to compute the slope. Let's pick this point right here. Let's see, this has coordinates 30, 100, and this point down here has coordinates 0, 20. Let's see, I'll call this we'll call this point 1 and maybe call this point 2. Okay, so then M is going to equal the ratio of the change in y to the change in x. So let's see here. I'll write out the formula, y2 minus y1 over x2 minus x1. Let's see, so y2 is going to be 100, y1 is 20, x2 is 30, and x1 is 0. So we get 80 over 30, or 8/3. 3 goes into 8 twice with a remainder of 2, so this is 2 2/3, or 2.6 repeating in decimal. Okay, so we have our slope. Let's see, here's a little fill in the blank problem. If the blank of ski goggles increases by blank, then the total cost will blank by blank. Okay, I think what they're getting at here is if we increase the ski goggle count by 1, then the total cost, what happens to the total cost then? So if I think what we want here is the quantity. If the quantity of ski goggles increases by 1, that looks kind of like a 7, by 1, then the total cost will increase because our slope is positive, increase by $2.67 approximately. So I'll write 2.66 and I'll put a bar over that last 6, which means it's a repeating 6, right? All right. Okay, so that's how we interpret it, right? Because what is the slope? It's another way to think of it is rise over run. In other words, if we increase the run amount, which is quantity of goggles produced, if we increase that by 1, then the cost, the output variable, will rise by $2.66 approximately. Okay. Give a linear equation for the total cost to produce X ski goggles in the form C of X is equal to mx plus b. Okay, well, we just computed m, but what is b here in this case? Well, let's go to the original bit of information they gave us, which was in graph form. Now, recall that mx plus b is called slope-intercept form because m is the slope and b is the y-intercept. Well, what is the y-intercept? It's this point right here, which has a y value of 20. So b is 20. So then our cost function would be c as a function of x, cost as a function of quantity is going to be, do I write it as a decimal or a fraction? I'll write it as a fraction, I think. 8/3 x plus 20. Okay, part D. What is the total cost to produce 120 ski goggles? So that's what our cost function is for, computing total cost, right? So we want to compute C of 120, or in other words, we want to evaluate this function at a production level of 120 goggles. So we bind the value 120 to the symbol X and then evaluate. Let's see, 8/3 times 120, well, 3 goes into 120 40 times. So that's going to be 40 times 8, which is 320, plus 20, or 340. So it's going to cost us, I'll put the units in there, $340 to produce 120 ski goggles. Okay. Okay, the next exercise. Catherine invested some money in a friend's small business. The value of her investment is given by the function b of t is equal to 7,150 minus 95t, where time is measured in years. So I think t denotes time here. This function tells us that Catherine's initial investment was valued at blank dollars, and that the value of the investment is blank, and we're given the choices increasing or decreasing at a rate of blank. Now this function is a linear function, and it's in that we're not using x here, we're using t as the independent variable. And the y-intercept is 7,150. The slope is negative 95 here. So notice that if we set t equal to 0, that will give us the initial value of her investment. And when we set t equal to 0 in this function, we just get out 7,150. So that's the value of the initial investment. It's the y-intercept. If we were to graph this function, that's the y-intercept. Okay, now because the slope is negative, as time increases, the value will go down because the rate of change is negative. So the value of the investment is decreasing. And decreasing at a rate of 95, well, what are the units there? It's going to be, it doesn't say exactly, so we'll just say the rate is at 95. We don't know the units. It could be dollars, it could be thousands of dollars, it could be, maybe she's very wealthy and it's millions of dollars or something, I don't know. Okay, next one. Last year, the Razor Scooter Company introduced a new scooter. It cost $5,200 to develop the scooter and $35 to manufacture each scooter. Part A, write a linear function C of n is equal to mn plus b that gives the total cost to produce n scooters. Okay, so n is our independent variable, m is the slope, and b is the y-intercept. And in this context of a cost function, the y-intercept is the fixed cost. It's the amount you have to spend in order to start producing these scooters. And that was $5,200. We had to spend $5,200 to develop the scooter, and it's just a one-time fixed cost. So that's our B value. And then the cost per scooter is $35. And notice that has 2 units to it. It's dollars per scooter. So that's a rate of change. That's our slope. So our cost function here, C, is a function of n, is going to be 35n plus 5,200. Okay, let's use that function in part B here. What is the total cost to produce 2,900 scooters? Okay, let me pull up the calculator. We want to do 35 times 2,900 plus 5,200. I get $106,700. Does that seem reasonable? Yeah, that seems reasonable. Okay, part C. How many scooters can be produced with a budget of $115,450? Okay, so here we know the cost that we're willing to spend, and we want to figure out the quantity that would correspond with. And what do we have? We have a function that relates cost to quantity, but we know the output of the function, and we're trying to get the input. So what we're trying to do here is solve this equation. C of n is equal to $115,450. But this C of n is equivalent to the expression 35n plus 5,200. So really what I want to solve is this equation, 35n plus 5200 is equal to 115,450. Okay, now, yeah, and then if I solve this equation, it's going to give me N, the quantity, the number of scooters that we can produce given that budget. Okay, to solve the equation, I need to subtract 5,200 from both sides. Let's see, I'll use the calculator again here. We want to do 115,450 minus 5,200. Okay, 110,250. So we get 35n equals 110,250. So I want to divide both sides of the equation by 35. Let's pull that calculator back and take that result and divide it by 35. I get 3,150. So N equals 3,150. Yeah, that seems reasonable. With the previous answer, we got, for a budget of $106,700, we got 2,900 scooters for another almost $10,000. We're going to get another 250 scooters. Yeah, okay, that seems reasonable. All right, let's move on then. By the way, it's always a good idea to do some sanity checks on your work like that. Just start comparing your answers to what you think you should get. And see if it just seems like a sane value to you, you know, a sanity check. Okay, let's see here. A clothing business found that there is a linear relationship between the number of shirts, N, it can sell, and the price, P, it can charge per shirt. In particular, past data shows that 9,000 shirts can be sold for a price of $53 each, while 10,000 shirts can be sold at a price of $44 each. Give a linear function of the form P is equal to Mn plus B that gives the price P they can charge for N shirts. Okay, so we want a function that relates price to quantity. Price and quantity. Whenever you think of a function that relates price and quantity, you should think of supply and demand. So this is going to be, I think this is going to be a demand curve, because they did research on the market and found what the market is demanding, right? We'll talk about that more in just a moment, but so we want to get a linear function, and it looks to me like I see 4 numbers in the problem. 4 numbers, that should clue me in. That's enough data to get 2 data points, right? 2 points on the graph. Yeah, so let's see, what would those points be? They found that they can sell 9,000 shirts for a price of $53. Okay, we got to make sure we put these points in the correct order too. So if we look at this function, P equals Mn plus B, N is the independent variable and P depends on N, the quantity. So price depends on quantity. So the number that comes first is the quantity, the number that comes second is the price. So the research showed that at a quantity of 9,000 shirts, they could fetch a price of $53. And it also found that at a quantity of 10,000 shirts, they could fetch a price of $44. All right, so we have 2 data points. Once you have 2 points, we can get the equation of a line. But it's a 2-step process. We're going to need to get the slope using the rate of change formula. And then we're going to have to use the point slope formula to get the equation of the line in that form. Okay, so first step is to compute the slope. I'm going to call this point 1. I'll call this N1 and I'll call this P1. I'll call this N sub 2 and P sub 2. So this will be my second point. And my slope is going to be the change in the output variable, which we're denoting with P, divided by the change in my input variable, which we're denoting by N. In other words, we want to do the difference here. P sub 2 minus P sub 1 over N sub 2 minus N sub 1. Okay, P sub 2 is 44. P sub 1 is 53. N sub 2 is 10,000. N sub 1 is 9,000. Okay, 44 minus 53. Well, I'm just going to do 53 minus 44. That's a difference of 9. But now I got to change the sign. It's negative 9. 10,000 minus 9,000, that's 1,000. Okay, so there's my slope. Now that I've got my slope, I have a slope and I can use the slope and a single point on the line. Doesn't matter which one I pick, any one of them will work. But I can use a slope and a point to get the equation of the line via the point slope formula. Now, normally when we write down the point slope formula, we usually write it down in this form. I'll write it over here. Y minus y1 is equal to m times x minus x1. And recall, this really just comes from the rate of change formula, right? If I divide both sides of this equation by x minus x1, I'm going to get m is equal to y minus y1 over x minus x1. And xy here just represents any point on the line. It could be the other point. But instead of using y and x, we're using p and n. So the corresponding formula that we want to use is, well, what would it be? It would be p minus p1, because price is our output variable. We're still using the symbol m for the slope or rate of change, but now we're using n for the input variable, so we're going to do n minus n1. So in our context, this is the point slope formula that we want to use. The point being n1 p1, the slope being n. Okay, now we have both of those bits of data. We can just plug numbers in and solve for p, and then we'll get our function. Okay, so let's plug in, I'll do it over here. P minus P1, that's 53. This is equal to the slope, which is negative 9 over 1,000 times n minus n1. n1 is 9,000. All right. Now we need to simplify this and solve for p. First step I'm going to do is I'm going to distribute that negative 9 over 1,000 to both terms in the parentheses, and I get negative 9 over 1,000 times n. And then when I multiply negative 9 over 1,000 times 9,000, if you're unsure, just write it out, When in doubt, write it out. So 1,000 goes into 9,000, and I'm left with a factor of 9. So I have negative 9 times 9 over 1, or negative 81. But negative times negative is positive, so this is going to be positive 81. So P minus 53 is equal to that quantity. So my last step here will be to add 53 to both sides of the equation. So when I do this, what do I get? I get P is equal to negative 9 over 1,000 times N plus, let's see, what is 81 plus 53? That's going to be 134, so plus 134. There we go. What this function does is it models yes, it models the demand curve. So let's just make sure that we're right. So we did a lot of computation here. It's a good idea to check your work, and one good way to check your work is to use a graphing function. I don't have the calculator emulator software installed yet, so let's go ahead and use Desmos. So I'll go to the browser, and we'll go to desmos.com. Desmos.com is a JavaScript graphing utility that's really easy to use. There we go. Let's say P as a function of N is equal to negative 9 over 1,000 times N plus 134. Okay, let's see. Now I saw some stuff appearing in the graph area over here, but then it kind of disappeared. I think that's because I've got a really small number there for the slope. So let's see if I zoom out. Oh, there we go. I see the graph now, that red line. Let's see, but I want to change my scale now on the x-axis because the slope is really, really shallow. So let's change the y coordinates. In fact, let's change the x ones as well. Let's go from, say, an x value of, let's go from 0 to maybe 150. And then let's go y 0 to, our outputs were in the range of 9,000, 10,000, so I think we should probably go, wow, to at least like 10,000. Let's try 20,000. Okay. Oh, I mixed that up, didn't I? Yeah. Our x values are in the 10,000, 0 to 10,000 range, and our y values are in the 0 to 134 range. So let's fix that. 0, we'll go 150 here for price. There we go. I can see the function. Again, I'm making progress. And our x values will range from 0 to, say, 10,000. Okay, there we go. I'm not getting the whole graph, so maybe if I go to, say, 15,000. There we go. Okay. Now let's zoom out a little bit. Okay. Yeah, I had to change my x scale dramatically in order to get the relevant parts of the graph to fit on the screen, didn't I? Okay, now we can check our function by plotting some points, right? We know that the point when the quantity is 9,000, the price was $44 per shirt. Or no, $53 per shirt. There we go. Okay, I plot the point, and yep, it's on the line. So that's good, a good sign. We also knew that the point, when at a production quantity of 10,000, the shirts could fetch a price of $44. Yep, there we go. That green dot is also on the line. So, yep, what that means is that the equation of the line that we computed is correct. It satisfies those two data points. So we're good. Okay, and well, let's talk about what this curve means too. So this is clearly a demand curve. Okay. Why do I know it's a demand curve? Well, demand curves always have this negative slope, whereas a supply curve always has, it's always an increasing function, or usually always an increasing function. It's, for the most part, it's going to have an increasing trend to it. Okay, whereas a demand curve will always have a decreasing trend to it. Why? Because, well, when the price is very high, so notice that if the price were, what is this point right here? Let's put at a price of $134 per shirt, the market is going to demand 0 shirts. No one's going to buy these shirts at $134 per shirt. But as the price starts to come down, like here's a point on the curve right here. What is this point? So at a price of 80, just over $80, the quantity demanded will be about 5,900 plus shirts. Okay, so as the price comes down, the amount ordered, the number of orders that apparel companies will put in for the shirts will increase. Okay, so demand curves always have a negative slope to them. Okay, let's get back to the worksheet. Okay, an online retail company tracked the total number of monthly purchases. In March 2018, there were 3,520 purchases, and in March 2019, there were 3,040. Okay, I see 2 pairings of numbers there, right? Although they're not quite numbers, they're dates and numbers. But so that sounds like 2 points on a line to me. Assuming the total number of online purchases follows a linear model, so we're making an assumption here, answer the following. Find a linear function, s of t is equal to r times t plus I, where s is the number of purchases and t is measured in months, where January 2018 corresponds to year, I think that should really be month 0, right? We're measuring time in months, so that's a typo there. That should be month 0. Okay. So let's see here. We've got 2 data points. The first relates, and by looking at the form of the function we want t to be our time measured in months to be our independent variable. In other words, the variable that comes first, and s, the number of online purchases to be the dependent variable, or the variable that comes second in a coordinate pair. So we're going to create t comma s pairs. And our first t comma s pair is the March 2018. Well, I don't know how many months that is, so I'll hold off on putting a number there. But the number of online purchases was 3,520. And then the second pairing relates March 2019. So for right now, I'll just write 3/18. And here I'll write 3/19. That gets related to the number 3,040. There were 3,040 online purchases in March of 2019. Okay, now what I need to do is figure out, I can't use dates for a function. I need to use a number, and what we're doing is we're measuring time in months, where January 2018 corresponds to the year t equals 0. So a little thing to watch out here for is we're starting counting with 0 instead of the normal 1. Okay, and this is a perfectly fine way to count, but it can lead to what computer scientists call, and computer programmers call, off by 1 errors. Okay, because we're starting at 0 instead of 1, like we normally do when you start counting. When you start counting, you say 1, 2, 3. Well, here we're going to start counting with 0. We're going to do 0, 1, 2, 3. What I mean is this. The months of the year are January, February, March, April, May, June, July, August, September, October, November, December. So we're calling January 1st, that date will correspond with 0. And then February 1st will correspond with 1. March 1st will correspond with 2, and then so on and so forth. So the month of December 1st will be 11. So then March of 2018, we don't want to put a 3 here because we're counting starting from 0. What we really want is we want to use 2. Okay, so we want to use a 2 here. So that's what I mean by off by 1 errors. It would be very easy to think, oh, I should put a 3 there because March is the 3rd month. Well, yes, but we're not counting starting with 1. We're counting starting with 0. So in that way of counting, it's the 2nd month of the year. So similarly, March of 2019, how many months past January of 2018 is that? Well, that's a whole year. That's 12 months plus another 0, 1, 2, right? So that's going to be 12 plus 2, or 14. So the number here we should use is 14. In other words, March of 2019 is exactly 14 months after January of 2018. Okay, so there's our 2 points. Now we can compute the rate of change, or the slope of the line. They're using the symbol R in this problem, so I'll stick with that and use R. This is going to be the change in the output variable divided by the change in the input variable, or S2 minus S1 divided by T2 minus T1. Let's see, I'll call this T2 S2, and I'll call this T1 S1. So then this will be 3,040 minus 3,520 divided by 14 minus 2. Okay, I think I'll pull up the calculator to compute that. So we're doing, let's see, 3,040 minus 3,520. It's negative 480. 14 minus 2 is just 12. And 12 goes into 480. Oops. Oh, what did I do? I don't know. So we have 480 negative divided by 12. Negative 40. Okay, I should have been able to do that in my head. But doesn't hurt to use a calculator sometimes. Okay, so we know the rate or slope of the line. Now we need to use the point slope formula to get the equation of the line or the function. And so in this context, it's going to be s minus s1 is equal to the rate of change, which we're calling r, times t minus t1. So we have s minus 3,520 is equal to negative 40 times t minus 2. Okay, I'm going to come over here and finish this up. So we get s. I'm solving for s. But first, I want to distribute that negative 40 on the right-hand side. So I get negative 40t plus 80. Now I need to add 3,520 to both sides. 3,520 plus 80 is 3,600. So I get s is equal to negative 40t plus 3,600. Let's do a sanity check. What happened to online monthly purchases? From March of 2018 to March of 2019, they went from 3,520 online purchases to 3,040. So they decreased. So the fact that we have a negative slope seems reasonable to me. And since 3,520 is pretty close to 3,600, and we're just 3 months off, that seems reasonable to me too. The intercept. Okay, part B, interpret the slope of the model. Each blank sales are at a constant rate of each blank sales are at a constant rate of each month sales are decreasing at a constant rate of 40. So each month sales are decreasing at a constant rate of 40. And the units here are not dollars or anything. It's just a pure number of sales. Okay, part C. What will be the monthly sales in December of 2019? Okay, so 2019, that's a full year after January of 2018, which is month 0. So how many months after January of 2018 is December of 2019. So it's a full year, 12 months, plus the 11. Remember, December is related to 11. So December 1st of 2019 will be 12 plus 11, or what is 12 plus 11? That's 23. 23 months. So we want to compute S of 23. So S of 23, that will be negative 40 times 23 plus 3,600. I think we'll pull up the calculator for that. So 40 negative times 23, times 23 plus 3,600. I get 2,680. All right. Okay, in which month will sales reach 2,000? So I know the output. I want to get the input value. So in other words, I want to set my function equal to the output value and solve for time. So I want to solve negative 40t plus 3,600 is equal to 2,000. I subtract 3,600 from both sides of the equation, and I'm going to get negative 1,600 on the right-hand side. Divide both sides of the equation now by negative 40, and I get t is equal to, I'm just going to use the calculator here. My brain is hurting. So let's see here. 1,600 divided by, it was 40? My brain is really pooping out on me right now. Yes. Divided by 40 is 40. Okay. I thought so, but for some reason I doubted myself. Doesn't hurt to check. Okay, so 40 months past January 2018. So what month is that? Well, if we divide 40 by 12, that's going to give us the number of years, plus the remainder will be the number of months, right? And of course, 12 goes into 40 3 times, or in other words, 40 equals 36 plus 4, and 36 is 3 times 12. So 40 months is a full 3 years and 4 months beyond January of 2018. Not just 4 months. We got to use our counting system where we start counting from 0. So that would put us, if I go back here to my little thing here, the 4th month corresponds with not April but May in this counting system. So the answer is we will hit 2,000 in online sales in May of, let's see, 3 years beyond 2018 is 2021. May of 2021. Okay, there we go. So you got to be careful when you start indexing with, sometimes we call this indexing with 0. The idea is you just start counting with 0 instead of 1. So it's a little bit tricky, but computer programmers use it very frequently because it makes calculations simpler often. But you do have to worry about being off by 1. Okay, next exercise. You are planning to start a new volleyball club in Salt Lake City and have just concluded a marketing study. From the study, you have determined that the quantity of members Q to join your club will depend on the price P of membership. That is, Q is a function of P. At a membership price of $70, you can expect 120 members to join. Okay, that looks like a pair of numbers to me, 70 and 120. And at a price of $65, you can expect 150 members to join. That's another pair of numbers, isn't it? Okay, so what are we doing here? We're relating a quantity to a price. Often in economics, we make price the output variable and quantity the input variable, but you don't have to. And this one's doing it in reverse order. It's saying that quantity is a function of price. Okay, perfectly fine to do that. Let's see here. Find a linear function Q of P to describe the quantity of members as a function of price. So we need to use the 2 data points they gave us. So our data points are going to have this form because P is the independent variable and Q depends on it. Our points will have the form P, comma, Q. So they're going to be a price and a quantity. So the first one will be, what was it? At a price of $70, we can expect 120. The quantity of members will be 120. And at a price of $65, we expect 150 members to join. Okay. Let's see, I'm going to call this point 1, so this will be P1, this will be Q1, and this will be point 2, so this will be P2 and Q2. Okay, and the first thing I want to do is get the rate of change between these 2 points. I'll call it M. This is going to be delta Q, the change in the output variable divided by the change in the input variable. Or in other words, Q2 minus Q1 divided by P2 minus P1. And you might think it's kind of silly that I keep writing this over and over again, but I don't think it is, because it's guiding me, and I don't have to think as much if I always write it out. Okay? Now it's just a matter of plugging in the numbers, and so less thinking, less error prone. It's more mechanical. When you make problem solving as mechanical as possible, it's less error prone. In fact, until you get to the point where you can program a computer to do it, and you can do it perfectly every single time, right? So let's plug the numbers in. So we have 150 minus 120 over 65 minus P1 is 70. Okay, well 150 minus 120 is 30. And 65 minus 70 is negative 5. So this is negative 6. That's our rate of change. Okay. Now we need to take the slope and a single point, plug it into the point slope formula, which in this context is going to be given by the output variable q minus q1 is going to equal m times p minus p1. Okay, so q minus q1 is 120. Our slope is -6. P minus P1 is 70. Okay. Okay. So what this function does is, what does it say? It relates the quantity of members we expect to join as a function of price. Now, as price increases, what do we expect? We expect the number of people to join to decrease as well. And that's exactly what happens because we have a negative slope. Okay. So let's see now. Interpret the slope of the model. For each blank of $1 in the price of membership, we can expect that number of members to decrease at a constant rate of 6, right? So for each increase, so as price increases, for each increase of $1 in the price of membership, we can expect the number of members to decrease at a constant rate of 6 members per dollar. So every time we increase the cost of membership by $1, we're going to lose 6 members. Okay, part C. What is the quantity of memberships expected if the price is $50? So here we want to evaluate our function. So we want to evaluate the function q as a function of p at the price of 50. So this is equal to -6 times 50 plus, what was it? 540. So this is -300 plus 540, or 240. So when the price is $50 for a membership, we expect 240 people to join. Part D. What should the membership price be if you want 200 members to join? So we know the output is 200. What we want to do is set our function q as a function of p equal to that value, 200, and solve for p. We're going to replace q of p with the expression for the function, -6p plus 540 equals 200. Okay, I'll subtract 540 from both sides, and I get -6p is equal to -340. So p is equal to 340 divided by 6. I'll pull out the calculator for that. 340 divided by 6. 56.6 repeating. So P is equal to, this is a price now in dollars, so $56.67. All right. And this concludes section 1.4.